Today I'm going to be going over both of the physics test problems that we had. So I don't remember the exact values, but I'm gonna just estimate them, and I'm gonna show you like what the problems were about. So basically, the first problem consisted of basically there was like I forget if it's like a cannon or like a launcher, basically a wedge with a barrel on it that had a spring. And so basically the relaxed spring length I think was like around 0.4 meters, and the entire length of the wedge was, I want to say, 1.75 meters. And then the angle theta here, I'm pretty sure, was 38.5, maybe, I think. Yeah. And so basically, then it said a mass that was, I'm gonna just say 0.5 kilograms for simplicity. Um, because I think it was like 4.48 something 44, I don't really remember. And then it had the spring, um, with a spring constant, static spring constant of 5640, I think, newtons per meter. Okay, and so the problem was saying if they push this spring thing down with this mass on it, um, uh, to a fully compressed length of, I'm gonna just draw that down here, fully compressed length, I think it was around 0.1 less, it's like 3 meters, and then they let it go, and it's gonna, if we have like no friction or air resistance, it's going to take a circular arc and have a maximum height and a maximum length it travels. So the question was asking for what is the change in x here, and what is the basically y max value it reaches. So to start off this problem, we have to identify what strategy we're going to be using. I personally used energy. I think this is possible with forces, but a lot more complicated. So I'm going to be using energy, so I'm going to set up an equation to define a few heights. So I'm going to be starting from the compressed length of the spring. So I'll start with that, 1/2 kx squared. And so the compressed length of the spring, the mass will have a height that I'll label height 1. So then it's also going to have, if we set this as our reference, height equals 0, this will be height 1 above that. So it's going to have some gravitational potential energy of mgh1. So then we're going to try and find the velocity after it exits this barrel. So the velocity at this point, so we can calculate how far it goes. So we need the height at this point, which I'll label as height 2. So when it's exiting the barrel, all of the spring energy has been used up basically, because the spring will only travel back basically the opposite of how much it's been compressed, and it stops accelerating the mass at this point basically, and there's no friction, so the only thing pulling down on the mass is going to be gravity. So anyways, so when we are at the edge of the barrel, assuming this is a pinpoint mass, we're going to still have no kinetic or no spring energy, but we will have kinetic energy. So we're going to represent that as 1/2 mv squared. And then we also are going to have more gravitational potential energy. This time it's going to be mg height 2. So you might be wondering, how do we find height 2? Because we have our, okay, we have the distance that's compressed, so we just have to do a little bit of math for that. We have the mass, we have gravity, we don't have height 1. We have that, we're looking for velocity. We have that, and we know gravity. So we want to basically figure out what height 1 and height 2 are. So for height 1, what I'm going to do is I'm going to take the sine of the angle with the distance. So height 1, we know the spring is compressed 0.3 meters, so the pinpoint mass will be at 0.3 meters as its hypotenuse. So we could say height 1 equals, I'm going to do 0.3, and then we're taking the sine of that angle because we want this up and down length. So 0.3. Sine and our angle again is 38.5. So 38.5. So that's our height 1. And then for height 2, this time we're going to be using the full length of this wedge, basically. So from here to here, which is going to be basically the entire hypotenuse is going to be the entire length, which is 1.75. And we're going to again use sine to get the height component. So we can say height 2 is 1.75 sine 38.5, still the same angle because they are congruent. Or, yeah, I think congruent, similar. I don't know, whatever. So now that we have these two heights, what we're going to do is we're going to now plug it, verify our x value. So x is going to be how much the spring was compressed. So in this case, it was compressed from 0.4 meters to 0.3 meters, which is a difference of 0.1 meters. So x equals 0.1 meters. So now, these I guess are also meters, but it doesn't really matter. Now what we're going to do is we are going to plug in our values into our equation. So that'll give us 1/2. Again, this is just a lot of calculating. 5640, it's really easy to get numbers wrong. 40, and then our x squared is going to be 0.1 squared plus m each, not m. Mass is 0.5, 5 times 9.8. I'll just put parentheses to be consistent. 0.5 times 9.8 times height 1, which is 0.3 sine 38.5. And then that's going to be equal to 1/2 of our mass again, 0.5. Then I'm going to leave v squared here. And then we're going to add 0.5 times 9.8. And then height 2 is 1.75 sine of 38.5. Okay, so now what we're going to do is we're going to basically just solve for v squared here. So I'm going to simplify a few of these values by just adding all of these numbers together just to make it a little bit simpler. So 640 divided by 2 is going to give us 2820, and then multiplying that by 0.1 to the power of 2, which gives us a value of 28.2, and sets us in energy, so that'd be joules. So now we're going to add on the gravitational potential energy, which is 0.5 times 9.8 times 0.3 sine 38.5, and so that gives us a slightly bigger number. So the total of this half of the equal sign will be 29.11. Again, this is in joules because we're measuring the energy. And so then I'm going to just add all this together and then add all that together. This is 0.25. But yeah, so 5 or 0.5 times 9.8 times 1.75 sine 38.5. That is going to be equal to, on this half, 5.33, again in joules. So to isolate our v squared, I'm going to just take the number here, subtract it from there, and then divide that number by there. So 29.11 minus 5.33, and then over 0.25, square root of that, and that'll give us our velocity, which is the velocity exiting here. So initial velocity. So if I take the square root of 29.11 minus 5.33, and then divide it by 0.25, we're going to get a value of velocity initial of 9.75 meters per second. So this is slightly different than what I got on the test. But of course I'm rounding the numbers heavily, so it's going to be slightly different than the test answer. Honestly, for simplicity, I'm going to just say the velocity is 10 meters per second, just to not have to deal with all those decimals and stuff. That'll lead to more errors in future calculations. So now basically we're left with, we have initial launching point, which is going to be here, where we have a y initial and a x initial. So the launching point also has a velocity initial that we calculated on the other page. So we're going to break up this velocity initial into two things. Also we have angle. So VO sine theta is going to be the upward one, and VO, I'll choose that one because VO cosine theta is going to be the sideways one. So I'm going to start by solving for the max height it reaches. So this is going to be continue going up and then go all the way down. So at the maximum height, the important thing to note is that basically the velocity, the final velocity in the y direction is going to be 0. Because basically when we're at the top of this curve, that's where the velocity goes to 0 and then goes back down. So there's going to be one point where the velocity is exactly 0 in the y direction, and that's going to be the maximum height we achieve. So if we set up our reference for height here, I'm going to use a kinematic equation, v final equals v initial plus acceleration times time. I'm going to be solving for this value of time. So again, before I do that, I'm also going to set up our equation that'll help us find this final height. So I'll say y final, I'll just put an f because yf equals, we have our y initial plus initial velocity, which is going to be v naught sine theta t, and of course we have gravity, so plus 1/2 negative 9. I'll just say negative g just to make it sure. So basically now what we're going to do, we know what our final velocity is going to be at this top point, which is 0. And we know what our initial velocity is because we calculate on there, but that's of course the velocity in the y direction. So I'm going to say that this is a y equation just to make sure we understand that. And then we're going to be knowing the acceleration because that's just gravity in the downward direction, right? And so then what we're going to do is we're going to solve for our unknown here, which is t. So, I mean, you can't really solve for t in this equation alone because we have two unknown variables. So if we have two equations, what we can do is we can take the t from one equation and sub it into the other because they're representing the same point on the curve, basically. So what I'm going to do is I'm going to algebra this around, and we have t equals v final minus v initial over negative g. We know v final is just going to be 0, v initial is our y velocity component, so that's v initial sine theta, and then negative g is just negative g. So if we put in our values of VO sine theta, which will be from the other page, I'm going to use 10 meters a second. So 10 sine, and the angle remains the same because basically this angle right here is the same as that angle right there. So we still have our 38.5, and then we're going to divide it by 9.8. The negative signs cancel, and I'm going to put this into a calculator. 10 sine 38.5 over 9.8. And we get a time of, this is solving for time, remember, 0.635 seconds. So that's the time it takes to reach this. but we're not asked for the time in the equation. We're asked for the height, or the y final, y max. I probably should have put max instead, but yeah, y maximum. So what I'm going to do is now I'm going to take this value, plug it in for t in this equation, and solve for y. We already know what the y initial is because we know that this is 1.75 meters, so the y initial is equal to the sine portion of that, so that's 1.75 sine 38.5. We know what VO sine theta t is, that's just this value, or we can just say our initial velocity is 10, theta is that, t again is this, and 1/2 negative g, so it's negative 9.8 times 1/2, which is negative 4.9, and then we have our t squared, which again is just going to be this number. So I'm going to plug all these into my calculator, and so I get 1.75 sine 38.5, then we're going to add on our initial velocity, which we're just saying is 10 sine 38.5, and then we're going to multiply that again by our t, which is 0.635, and then I'm going to add 1/2 of negative g, which I'm going to put as negative 4.9, and then we're multiplying that by 0.635 to the power of 2. And when I press enter, that should give us a maximum height, or a y final, of, I don't know why I put of, equals 3.1 meters. So again, on the actual test, these numbers were a little bit different. I did some approximations with my numbers here. They were like all decimals and all like crazy and stuff, but yeah, this is still the process that we're going to be using to solve this equation, even if it isn't the exact same. So that is 3.1 meters for the y max, and the other question was, what is the change in x? So that means this to here, not the whole curve, because the whole curve would like continue down there. We just want the change in x. So I'm gonna start a new page. So this time it's going to be a little bit more complicated. Each side is ugly. Because basically we're going to still have our angle theta. We're still going to be 1.75, and we're still going to have our initial velocity, which is going to be going at our angle theta. But this time, we're still going to have VO sine theta and VO cosine theta. But this time we're going to be starting with a initial x position, which is just going to be equal to 1.75 cosine of theta. So 1.75 cos, and I'm going to just write 38.5. So if we set this as x equals 0, and then we set this axis as y equals 0, it's like height. This is going to be continuing around. Nope. More like this. So now we're going to have to use a combination of x and y to find the final velocity. And one more thing I'm missing is the initial y position, which is going to be 1.75 cosine of 38.5. So what I'm going to do is I'm going to set up two kinematic equations. So our first one, I'll start with the x. So I can model this either as change in x, or I can model it as x final. So if I do change in x, it'll give us our direct answer, and if I do x final, it'll give us the entire thing. So if I do change in x, that's going to be taking into account this value, and I'm going to have to basically add that at the end. Or I can do the final x, put it in the equation, and then I'll still have to subtract it. So it's up to you. I think I'm going to try and solve it right now with change in x, because on the test I did 1.75 cosine. So yeah, so change in x is going to be equal to, so because we're using change in x, that's already taking the initial x position into account. So it's going to be like inside of here basically. So I'm going to just say it is equal to the velocity in the cosine direction, because that's the x direction, theta times time. And because we're traveling in the x direction, it's not going to accelerate or decelerate at all. There's nothing pushing back on it like in the y direction, like gravity. So that gives us a pretty simple equation here. I'm gonna see if this actually works to just solve for change in x. So yeah. So now I'm going to be looking at the final y position, which I'll just say y final, yf. So this time I am going to take the y initial into account. Or you know what? Yeah, I'll take the y initial into account. So I'll say y initial plus we have our initial velocity in the y direction, which is v naught sine theta. And then again, kinematics, we're going to add a t because we're using the xo plus vot plus 1/2 at squared equation, and that equals x. Doesn't really matter. But this time we're also going to be including gravity, so that's 1/2 negative g and then t squared. So again, what I'm going to be doing is I'm going to basically be solving for our time here. And I'm going to plug it into this equation. What you could do also is solve for time in terms of this and then shove it all in there and then solve for x. But since we know what the y final position is, we don't really need to do that. So how do we know what the y final position is? Y equals 0, right? So that's our reference point. It's going to be crossing that. So that basically means the final position of the y is 0. So when we solve this equation, we're basically going to get two times. The time that's going to give us here and the time that's going to give us here. The 2 points that's crossing this. So I'll just set that to 0. So now we know our y initial is this horrible number. So 1.75 cosine of 38.5. And then I'm going to be adding on our v naught sine theta. I said that we're going to say the initial velocity, still the same, it's going to be 10 meters per second. And we have sine of 38.5, because the angle is still the same. And then we have our t, which we're solving for. And then I'm going to just put minus 4.9 t squared. So now what I'm going to do is I'm going to basically just put this into a quadratic formula and solve that on my graphing calculator. That's also, like, I feel like kind of an unfair advantage on this test to have a graphing calculator, because then if you have the program for the quadratic formula, then it's like a lot faster than like actually doing it by hand. But anyways, basically when I put this in, we get 2 times. We only actually care about once, so we get negative 0.191. So that's basically saying that like we went like this far back. That makes sense given this is like where we started from. And then we also have a time of 1.46 seconds, which is what we care about. So what I'm going to be doing is basically putting that into this equation over here. So the change in x will be equal to our initial cosine theta t, whatever. Theta is 38.5, and then our t is going to be 1.46 seconds. 6 seconds. So I'm going to see if this works. So 10 cosine 38.5 times 1.46. So that gives us a value of change in x of 11.42. So I am slightly skeptical of this, just because we didn't account at all really for the xo. So what I'm going to do just to verify this is I'm going to set up an equation for x final. So basically it's going to be x final minus x initial is equal to VO cosine theta t. So just to verify this number, I'm going to plug in our same numbers from there. So we don't know what x final is. We know what x initial is. So x final minus x initial, which we said was, I think, 1.75 cosine 38.5 equals VO cosine theta of t. So that is 10 cos theta is 38.5, and we determined our time to be 1.46. So I'm going to put that into a calculator. So basically 10 cosine 38.5, so 38.5, and then 1.46, and then I'm gonna add the other thing on the other side. So that would be plus 1.75 cosine 38.5. And so yeah, so basically this value that we get of 11.42 meters is actually the correct value. I verified that because basically I get an x final value of 12.79 meters, and basically we're subtracting that to get the change in x. So I just did a unnecessary step, I guess, also when I was solving it on the actual test. But yeah, so now I'm going to move on to the next problem, problem 2, which is, I think, just a lot less busy work than this problem, because we see the actual like physics isn't that hard here, but just like having all the numbers is kind of scary and kind of difficult. So the second problem starts with a Earth, which like with E, and then there is I'm gonna try and get the spacing right. There's a satellite, which I'll just draw arrow to and say S for satellite, and it is going to be orbiting the Earth in a circle. I know my circle drawing isn't very good, but it doesn't really matter. And we're given that the radius from here to here is 2 times the radius of the Earth. So the question is, how do you determine what the velocity of this satellite is? Because basically the satellite is going to be traveling in a basically straight line, right? And then there's going to be, we're going to label that VO, and then centripetal acceleration is going to bring it in. In this case, gravity is also playing a role in this. So the I think it's actually basically the gravity and centripetal acceleration balance out basically to maintain this perfect spherical thing. So that's the first part, what is the V initial, and then it's asking for what the time period T would be. So to figure this out, what I'm going to also do is just draw like a thing on S to represent the forces acting. So the only thing acting on it is going to be the force of gravity from the Earth. So I'm going to just set up some axes, it doesn't really matter. Just say that's positive. So basically we get negative FGE. You know, I'm going to just revoke my axes and then just say that's positive. Just to make this a little bit easier. So basically this is the only force acting on it. We know it's traveling in a circle. So basically, force of gravity from Earth is going to be equal to the mass of the satellite times the centripetal acceleration. So now all we have to do to figure out the velocity is to convert this into velocity and to convert this into an actual number, because it's asking for it in terms of g, radius of the Earth, mass of the Earth, and yeah. So we're only really allowed these constants or things to work with. So yeah, and any numbers. So to determine the force of gravity, we're going to use the laws of gravitation, I believe they're called. So basically, that's saying that the force of gravity on two given objects are basically, or in between, is going to be the gravity times the mass of object 1, and then times the mass of object 2, with the radius being the distance between them squared. So in this case we have two objects, Earth and this satellite thing. So we can use this equation. And then we're going to set that equal to, we know force of gravity of Earth. I'm going to say mass 1 is Earth, mass 2 is our satellite. Force of gravity of Earth, we already said, is equal to mass of satellite times the centripetal acceleration. So I'm going to put mass of satellite, and then I'm going to split this up into velocity. So v squared over r, that's the same as the centripetal acceleration. So now for solving for velocity, all we have to do is cancel our units. So mass of the satellite canceled on both sides. One of the r's gets canceled. I'll just cross out the 2 to represent that. So basically, we get v, I'm going to also square root it just to get rid of the square root. V is equal to the square root of g m e over r. The only thing is they want it in terms of radius of Earth. So the r in this case is the total distance between the center of the Earth and the center of the satellite. So that is our r. But what is that in terms of radiuses of Earth? Well, we know that the Earth has a radius of re, and it's also stated that the distance from the surface of the Earth to the satellite is 2re. So basically, we can take these, add them together to get 3re, which is we're going to replace for our r. So I'm going to just erase our r over here, and we have gme over 3 radius of Earth. And that is our final answer because they haven't given us any sort of units or not units, numbers to work with. Of course, you could figure this out if you knew the mass of the satellite and the mass of the Earth. You could figure out like the velocity. I guess you also need the radius of the Earth. But yeah. So now we're going to work on the second part of the problem, which is finding t, not tension, but the time period for one rotation of one rotation. So if this is traveling in a circle around the Earth, right, we know that this is basically going to be a circumference if it's a perfect circle. And we know the equation for circumference is equal to 2 pi r. So now all we have to do is figure out what r is. But wait, we already did that in the other equation. We just added radius of Earth plus 2re. See, r equals re plus 2re. So that'll give us a value of r of, no, not r, 3 times re. Re being the radius of the Earth, so this distance. It's like 1, 2, 3. So now instead of putting r, we can just sub that in. So circumference of satellite, which is just a path it takes, is equal to, I'm going to move the 3 to the front, so 2 times 3 is 6 pi, and then that's multiplied by the radius of the Earth. So this is the total distance it travels, right? So it doesn't give units in the problem, so I'll just say units, right? So now we know that our velocity is root of g me over 3re. So velocity is equal to root g being gravity, me being mass of Earth over 3r. So this is going to be velocity, so you know that is going to be units over seconds, or if we are even unsure about that, we can say over time. I'm going to just say seconds, because it's probably in seconds given every, like, mass, whatever. This numbers in terms of seconds each, I think. So, yeah. But this is basically units per second, but we want seconds. So, because we want the time of one rotation in seconds. So if we look at our units alone, we're going to have units and units in seconds. So to get seconds on the top, we're going to divide it by units over seconds. So basically these two cancel, and this gets flipped because it's divided twice, and seconds goes to the top. So that basically means we need to take this number and divide it by our velocity, which is gme over 3re. and that's going to be units per second. Units cancel. So our final answer is time period equals 6 pi radius of Earth over the root of g mass of Earth over 3 radius of Earth. So that is our final answer. We can say seconds. It's some time period, probably seconds, given we're using big G, which is the gravitational constant. So yeah, so that's basically the whole test. So if we notice, this problem is really, really similar to that other problem we did a few days ago. I also made a video about it, with the pendulum swinging around and then being cut at this point and then being launched a distance. It's asking for basically the exact same things. So essentially this is like the exact same problem, except instead of a pendulum we have just springs. So instead of starting with mgh alone, we now have 1/2 kx squared also. So yeah, and that's the same process basically, which is kind of tough to do in 15 minutes with all these calculations. Of course, you have to be like scrambling. But then this second problem has really no calculating in terms of a calculator that you have to do. So I think it's a lot more laid back in terms of having to plug in stuff into a calculator, because I feel like that's one of the most difficult parts of these tests. But yeah, that's basically going to be it. So thank you for watching if anyone actually ever watches this. And yeah, see ya.